Okay, correlation. So since there were no question about, can we limit the conversation to one? Thank you. Who's coming? Okay, just tell her to let me know after. That's fine. Okay. Excuse me. Hi. Thank you. So correlation. So we're moving away from classical hypothesis testing where we're comparing means against each other. We're moving now towards correlation where we're trying to find an association between two variables that are essentially normally distributed. And that's the huge distinction. So you remember how we had now previously, we had a dependent variable that was a scale variable that was continuous in nature. And we had as the independent variable on the x-axis, we had a categorical variable, which was if we had one and we compared that to a mean, that was a one sample test. If we had two samples, this was an independent categorical variable with two levels. That was a t-test. And now we have three or more of these levels. That became an analysis of variance that we've done within the groups and between the groups. So now we're moving further. Now we have two variables that essentially are continuous in nature. That means we're basically looking how are these two variables associated with each other. So we're basically meaning to understand this a dependent variable associated with an independent variable and find out how does one variable affect the other variable. Why is that relevant? Because you need to kind of determine which different variables will predict a dependent variable of interest. So if I have blood pressure, how is that affected by age, sex, race, whatever parameter you're interested in? So that's the end goal, right? At the beginning, there's correlation. Correlations are basically two variables. So we're meaning to understand whether two variables are to some extent related and whether they change in the same direction and the opposite direction. If one gets larger, gets the other one larger as well, or get the other one smaller. This is what we will do today. Important to keep in mind is when you find a correlation, that doesn't necessarily mean anything. And this is what's meant with correlation does not equal causation. And that's very important to keep in mind. So if you further your statistical education, you will get into the problem that you will find associations that may in a perfect world show you a causal relationship, but that is not necessarily true. So there are correlations out there, and we will talk about the spurious correlations. That's the technical term for it, spurious correlations, that are basically correlating at a very high level, at a very high degree, but they're basically meaningless. And this becomes in epidemiology one of the arts to essentially find out whether this is a real correlation that makes any sense, that is an actual causal relationship, or that is basically just one of these spurious correlations. The only way how you can really determine in a study design a true association that has a causal underlying relationship, that is a randomized control trial. Because you have equally distributed variables in each group, and then each group, due to chance, they're randomly allocated to each group. And this is how you can determine causality, because you have no effect of a third variable, because there's randomness between those groups. Otherwise, you will always have some third variable, some confounder that is part of this equation that you will not be able to account for. So this is what this slide means. Keep in mind, correlation does not equal causation. And the example we're going to be discussing later will make this very, very clear. So correlation is quantified. So there's a number on that. This number essentially is accompanied by a p-value because it will follow the rules of t-distribution. But the correlation coefficient per se is a number that ranges from -1 to +1. So basically +1 is a perfect correlation, -1 is a perfect inverse correlation. So again, remember, if you have a correlation, that means it determines whether one variable changes with the other variable, either positively or negatively. If it's positive, this correlation, that means one variable is getting larger, the second variable is getting larger as well. Inverse means one variable is getting larger, the second variable is getting smaller. So this is positive and negative. or positive and inverse relationship. What is important, and that I have seen being mixed up quite frequently, so I'm flagging this. The correlation coefficient gives you a marker, or gives you an indicator of the strength of a relationship, of a correlation. It is independent of its sign. So you need to look at the absolute value of that correlation coefficient. Just because it's negative, that does not mean it's not a strong correlation. So the strongest relationships you have with -1 and +1. And it gets smaller towards 0. If there's no correlation, it basically gets 0. So that's the weakest correlation. And then it goes in both directions and increases in strength, positive and negative. Good. We have talked to some extent already about correlations, and you have done already a scatter plot. We've talked about the relationships. We've talked about linear relationships and non-linear relationships. What you essentially see there is that you have variables that increase in magnitude when the independent variable. So here's the example. You have vocabulary size of H2. And the second variable, the independent variable that predicts or associates with the dependent variable, is the number of different words an infant heard, which now on the causal level may imply, but does not necessarily 100% apply, because correlation doesn't equal causality, means that if you talk to your toddler, he or she will have at H2 a better vocabulary. Makes sense intrinsically, right? It's like, so that causal relationship actually sounds kind of reasonable. But nevertheless, based on the correlation that we may find here, which is positive in nature, because the vocabulary size will increase with the increase of words that infant heard, is a positive relationship with likely causal relationship. Yeah. So that basically, how you look at this. So again, the scatter plot, remember from chapter 4, the graphic display of data. Each individual point here in that scatter is one toddler. So that toddler associates with a vocabulary size of somewhere 130, 140, and the words he or she heard was like somewhere around 90. So that's one individual. And you have, again, in the same format as we have had it before, we have now one variable and the matching variable right next to it. And this is basically what you did for homework 1. There you created scatter plots. So this is exactly the format that we will need for correlations to build such a scatter plot that will lead us to building associations. So now, as said, we also have negative correlations. In that case, the correlation coefficient is negative. That means if you have only as the independent variable, the proportion of homework copied increases. The final exam grade in the same fashion also decreases. So that's inverse. So one variable increases, the other one decreases. That's a negative correlation. The perfect correlation, which is the perfect positive correlation, is a correlation coefficient of +1. It's basically a line. If you fit a line through this, every point will be on that line. That's the definition of a perfect correlation, which you will never see. Exactly. If anybody shows you a correlation coefficient of 1 or -1, he or she is lying. That data doesn't exist. I've seen that once when I reviewed the paper. That was the only time I requested that I will not continue to review this paper unless the data is not shared with the statistician. So, but it's impossible. You will not see that in real life, because you got to keep in mind that you have a measurement error that by default already shows you a variability in each measure. So it's impossible that you have a correlation coefficient of 1. The perfect negative correlation, same principle. You have basically a straight line, fits all the points. For this correlation coefficient, we will do an example today calculating this correlation coefficient because it does make sense to understand why that correlation is calculated the way it is. because that makes you understand what null hypothesis you're actually testing. You have, nevertheless, you have for the correlation coefficient, you have again conventions. You have 0 to 1 is 0, 1 to 0 0.3 is a small correlation, 0 0.3 to 0 0.5 is medium correlation. Everything greater to 0 0.5 up until 1, logically, is a large correlation. For negative correlations, it's the same. You have minus 0.1 to minus 0.3, 0.3, minus 0.3 to minus 0.5, and smaller than 0.5, minus 0.5, sorry, would then be a large negative correlation. So now the question that you will be facing on the quiz, and don't fall into this trap, is like, which is a stronger correlation? Anybody? Yes. Right. Why? Exactly. It's the absolute value that determines the strength. Perfect. Thank you. So it's really simple, right? It's also, that's the beauty about correlation and regression. Regression gets a little tougher when we're actually building the function. But essentially, it's conceptually, it's a super easy test, and it's super insight-focused in research. Okay, misleading or spurious correlations. So there's a 0.91 correlation between ice cream consumption and drowning deaths. Do you believe this correlation? Why not? Well, not really. Why is that? I would almost bet that this correlation exists. But why? Correct. Why could that be? Kayla was first. Yeah, you touched on the point quite elegantly. So the thing is, in winter, nobody tends to eat ice cream, right? And in summer, the risk of drowning is just higher because you're more likely to be somewhere close to the water. You're more likely to be on the beach. You're more likely to go into the water. You're more likely to spend time in the water. And thereby, that's the problem. And now, just finish my point. That is essentially what I do in epidemiology. I see associations and I'm trying to tease out what is the truth. And that's actually an intellectually extremely stimulating process. And yeah, so in summer you have a greater exposure to water, thereby the number of deaths increases. But basically, the operative factor is the time spent in water. It's not the ice cream. But the ice cream independently associates with your exposure. So you determine, you distinguish between exposure and outcome. And then you have a third confounding variable that basically associates with exposure as well as outcome.
There's like an extra variable, confound variable that's not.
Exactly. So it is not really a spurious correlation, but it's a true correlation, but it's just not a causal relationship. It actually would act as a so-called instrumental variable that basically leads to another variable, and that other variable essentially leads to that. Yes. Oh, which video? Tell me again.
The one where you gave like those three things. The funny one. Like
the funny one.
Is this the same type of example?
It goes in the same direction. Yeah. So basically, so Macmillan had a couple of different things that he actually did, but yeah. So essentially, you cannot believe every correlation that you have not tried to somewhat rationally penetrate and find some causal relationship behind that. That's what he did. He also used a very small sample size, and because he extrapolated from the small sample size, the variable it's not really seriously to be considered. But yeah, it goes in the same direction. And you see analysis like that quite abundantly. Bluntly spoken, it's actually, you do in epidemiology what you would build, you build graphs. You build a so-called DAG, or directed acyclic graph, where you have an exposure and an outcome. You build a connection between those, and you say, okay, so that's my connection. Then you try to map out all other factors that come in until you're exposed to like this huge network of different associations. Then you try to tease out the strengths between all of them and determine which one is actually the causal pathway. So yeah, goes in that direction. So don't be convinced that ice cream eating causes death. That's, well, independently, that's in some shape or form, I guess, extreme measures. But yeah, it's basically a spurious correlation. So you have invisible variables. So you have essentially this scenario. You have the confounding variable C that associates with the outcome and the exposure. Good. The correlation coefficient. So it's Pearson correlation coefficient, named after William Pearson, who was a statistician in the 19th century, I believe. It is a statistic that quantifies a linear relationship. Also important to keep in mind, it's a linear relationship. You cannot build R's in correlation coefficients. Non-linear relationships, you use a different metric for that, which we'll discuss next time. It's symbolized by the italic letter R when it's based on a sample, or it is the Greek letter rho when it is for a population. So reserve the rho really exclusively for population studies. We will only work with R. So we only have sample data, as you know, right? So, but sometimes you see population studies. For example, if you have population studies where you have country level data, like we had the happiness score for the different countries of the world, that would be considered a population study. And there you could argue that you use a rho rather than an R. That follows the same layout. And that's the correlation coefficient arithmetic. So what do we have? We have essentially now a numerator and a denominator. What we're getting with the R is the association between two variables. This looks a little bit more complicated than it actually is, because what it is essentially, you have again your deviations. Right? You have a deviation of an individual X from a mean of X, which is your first variable. Then you have a deviation of the Y of one individual score of your second variable from a mean of Y. Gives you the deviation of the second variable from the respective mean of that variable. You sum these deviations up, but this time you do not square them. You multiply these deviations of both variables and you sum these products up. Why do you do that? And why is it important that you have that? Because essentially what you create with that, you create the direction. Because if you have the mean, so you have the mean of X and the mean of Y, that basically gives you an horizontal and a vertical line. If you calculate the respective deviations and you multiply them, minus and minus equals out, becomes a positive correlation. Plus and minus creates rather a negative correlation. So a negative numerator. So the numerator actually determines the direction. And then you're dividing it here by your square root of the product between the sum of squares of X and the sum of squares of Y. And that will always be positive. We know that the sum of squares is squared deviations. You sum that up, that will always be positive. So this does not affect the direction. Just the numerator determines the direction. The sum of squares, essentially the denominator, determines how much is the variability. And if the variability is high, the sum of squares will be high, irrespective of the square roots. The denominator will be high. And as soon as the denominator gets high, your your final quotient, your R, will basically be small. So numerator gives you the direction, and the denominator gives you the variability, the factors in the variability. The consequence of that and the resulting indicator is the R. That's your correlation coefficient determining the strength of your association. And we will let's bring this over. So I have now, in addition to that, you have on your module, you have the spreadsheet, of course. This module comes with an exercise, because I think it's important to calculate this through. Only when you have calculated it, it's really clear why and how this basically presents it that way. So this is the R. For the rest, we're basically looking again at the same 6 steps. We identify the population, distribution assumptions, state the null research hypothesis. What is now the null hypothesis? The null hypothesis is the opposite of the research hypothesis. The research hypothesis is that one variable changes linearly with the other variable. So you essentially want this. Let's play around a bit with it. In essence, what you want is this. 2, 5, 6. This is what you want at the end of the day. You want inserts and your scatter plot. This is your perfect correlation. And not this, because that would be no. This would basically be your null hypothesis. So this is where X always is your independent variable, whereas the Y is always, so the X is always the first row, the first column. That's your independent variable. The second variable, the second column is your dependent variable. So this essentially would be your null hypothesis. So you're testing essentially against the null hypothesis that there's a stronger relationship between these two variables better than the mean of Y. So your null hypothesis is a flat line, because this is when X minus mx and Y minus my as a product divided by the variability is essentially the smallest. So now this as a calculation. So null hypothesis, okay, let's go back to the null hypothesis. We have the null hypothesis that there's no change with the dependent variable, with the change in the independent variable. To determine the characteristic of the comparison distribution is when we're calculating variabilities and standard deviations of means and the sum of squares between either. Then we determine critical values of cutoffs. And this is done with, of course, there's a table. There is this. There are two ways how to get this. So there's firstly, and this is, I'm just showing this. No? I'm just showing this for you to have seen it and have it on a recording. So you basically, in the knowledge of your R and the knowledge of your sample size, -2, you essentially have now the possibility to determine a t-score. And that t-score has, like every other t-score, it has essentially a critical value. The difference now is with your t-score, your degrees of freedom are now calculated differently because now you have to subtract 2 rather than 1. Because you have now, so student, forget student, this is not a variable, this is just a unique identifier, but you have 2 variables. You have, consequently, you have 2 sum of squares. And remember, the definition of the degree of freedom is the sum of squares and the associated data minus that 1 that in the knowledge of the sum of squares you can drop because you can arithmetically derive it. And this is basically the next step that you will use. Then you calculate the test statistic, that's your R. And based on your critical value and your test statistic, you make a decision whether there's a correlation or not and whether you reject the null hypothesis or not. So it's essentially simple, right? So the way to calculate that, okay, so the null hypothesis H0 is no change of Y with change in X. And now HA would be a linear change of Y with a change in X. So based on that, we're calculating now next our averages. That's just the same approach as always. We have now 3.4 absences in our sample and 76 average exam grade. Next, we're calculating our deviations or squared deviations. It's the squared deviations right away. So absences becomes now X. So X minus MX squared is now essentially this minus this locked in squared gets us our sum of squares X. So this is SSX. So this is now sum of these. So now we can just copy this over there and change this to D13. So this is D13 now. That gives us our sum of squares Y. And knowing these 2 values is basically already half of the accomplished exercise. Because now the only thing we need to do, we need, lastly, we need now the numerator. Again, the numerator is the sum of the product of the deviations of X multiplied by the deviations of Y. And that product is super simple to essentially calculate. So this is X minus MX multiplied by Y minus MY. So this is now X minus MX locked in multiplied by Y minus MY. Minus MY. So that's the product. And once you have the product, you just have to calculate this all the way down. And this is now each individual point. And you get for each individual point, you get a contributed product of the deviation. And now calculating this sum of products gets you essentially now to your numerator. So now the only thing you need to do is you take the sum of products, which is, as you see already, you basically see a negative sign. So you know already it's an inverse relationship. So you take the sum of product, you divide it by your sum of square. You divide the sum of product divided by the square root of the product of your sum of squares. That's your variability. This will determine your the strength of your relationship, strength of your correlation. It's an inverse relationship, and it's quite a strong association. So the conclusion of this is essentially that the greater the number of absences, lower the exam rate, which is an association that does make sense in principle. And always start with a scatter plot. Yes, they do have a good point here. So what we have done a scatter plot, so we know how to do scatter plots, but again, just to make sure that we're doing it in the same fashion, we're building now a scatter plot by just selecting B and D. Now we go and insert scatter plot. That gives us now the same scatter plot as Nolan and Heinzen have did. What is new? So we have. So now what we need to do is always make sure that you have labels. So basically, you want to label the axis. You want to say these are the absences. Count. You want to know that this is basically labeled correctly with vertically. As exam grade. Percentage. That basically captures now this association that you have. You add a trend line. That gives you a linear trend line. And if you double click the trend line, you can also add the so-called R squared to your association. And I'm just in preparation for next class. The R squared is in a univariate analysis only. And that's important to keep in mind because you have a univariate and multivariate analysis where you have several independent variables predicting one dependent variable. Only in univariate analysis where you have one X and one Y, one dependent, one independent variable, R squared, capital R squared, or proportionate reduction of error, which is consistent with the effect size in an ANOVA, can be calculated as the squared R. Gets you the same value. Alternatively, if you don't want to calculate it by hand in Excel, there's also the so-called choral function. The choral function with array 1 comma array 2 gives you the same result. Okay, so once again, you build your squared deviations, you sum them up, you get to the sum of squares. Easy. You calculate the product of the non-squared deviations, just the deviation of an individual x from an mx. You multiply it with y minus my, gets you this product of this non-squared deviations. You sum these up, gets you to the sum of these products, which is essentially your directional complement. This is your numerator. You have then lastly you have this numerator divided by the square root of these sum of squares, which is essentially if you build it is a combined marker of the variability. So it's the ratio between the product of your deviations over the square root of the product of your variability from mean of x versus mean of y. This gives you the strength of an association. So if we were to calculate now the t, we can do this quite simply. So you also have on Canvas, on the module, you have on the module, you have also the R table. So the R table is essentially a modified version. So the degrees of freedom are calculated by the sample size, which is basically the number of entries, which was for our exam and absence example 8. So we have 10 students minus 2 for each variable that you're testing in the correlation. You have 1 entry. So 10 minus 2 is 8. At an alpha level of 5%, you basically would need to have a correlation coefficient of 0.549. Have a significant correlation. So that is your critical R. So critical R is 0.549. If you were to calculate this now, you would do this by calculating your T would be your correlation coefficient multiplied by the square root of n minus 2, that's 8, n minus 2 divided by 1 minus the correlation coefficient squared. Gets you a T, and we're going to set this to an absolute. Absolute T. Gets you to a T of 4.85. If you would like to alternatively look this up in a T-score table. Let's see. We need to go back to T-score table. So 4.58. So we have degrees of freedom of 8 with 4.58. We're significantly exceeding our critical T 2.31. And the reason for that is because you again assume it's a normal distribution, but the sample size is smaller than 30. It's not normally distributed. You don't have this variability. The sum of squares is not given. You don't have this information. You're estimating it from your sample. You're using entity distribution. So the underlying distribution for your correlation is again the T distribution. Yeah. Good. So correlation is considerably simple. It's not really a difficult calculation. Regression is going to be a little tougher. But keep in mind, again, so you have your numerator gives you the direction as the sum of the products between the deviations of x and the deviations of y, divided by the square root of the product of sum of squares x and sum of squares y, which will always be positive, thereby preserving that direction that you get from the numerator in which the correlation is pointing at, if it's a positive or negative correlation. Dividing it by a marker of the variability, which is sum of squares x and sum of square y, in a modified version by multiplying it and taking the square root, you basically get a mark of the variability that determines the strength, and the larger the denominator and the larger the variability, the smaller you are. Good. Clear? Any questions? That's pretty simple. So then let's continue. So we know now that there's an inverse relationship between absences and the exam grade. Just here. Two. Yes. So it's the sum of the products of the deviations is divided by the square root of the product. Calculation has a built-in standardization procedure, subtracts a mean from each score divided by some kind of variability. Using the sum of squares in the denominator, it takes the sample size into account and determines as such the strength of the association. But this is not where this stops. So I also talked about multivariable regression. So you also have something that is called partial correlation. That means that you essentially, if you correlate two variables, that is not your whole story, right? So we talked about the ice cream example. If you have ice cream and ice cream alone does not determine drowning, it may, if you eat too much to it, maybe you eat so much that you can't move after that anymore, but basically this is not how this works. So it's really that association with the warm weather and the time in the water. So that's your third variable. So you can now, in correlation and regression, you basically can attribute the weight of the importance in the prediction of your dependent variable. This could be done by standardizing these respective variables. And this is essentially what partial correlation is. So not a causal relationship cannot be explained by just two variables alone if there's a third variable involved. So you basically, you get now association between two variables, and you have now the possibility to tease out what's the weight of each of these variables, and you can essentially come to a percentage of contribution to that dependent variable. This is, can be displayed by a so-called Venn diagram. So here you have, for example, this is the percentage of completed homework assignments with three different variables. So you have longevity in years, years of education, and weekly hours of tennis. So each of these three variables will have some effect. So with longevity, if you're older, you're likely more focused on your outcome of basically achieving your academic aims. That makes it more likely that you will complete your homework. With advanced years of education, which correlates also with the longevity, logically, this will also more likely contribute to the percentage of completed homework. And thirdly, the weekly hours of tennis may have a detrimental effect, may have a negative effect on the percentage of completed homework. So each of these three in total will essentially build up an explanation of your actually completed homework. So this is what partial correlation essentially is. Overlapping variabilities is this associations between all three of them. Does that make sense? Any questions? It's kind of clear, right? So the Venn diagram is actually a very nice way to depict these intersections, because essentially you have here three different fields where basically here you only have the intersection between years of education and weekly hours of tennis. Whereas here you have the intersection between longevity in years and weekly hours of tennis. And here you have the intersection between all three of them. So this is the individual contribution of the all three. And this is the rest of unexplained variability, essentially. Good. Any questions on partial correlation? So lastly, we're getting now to correlation in psychometrics. This is where it's getting a little bit more complex. So basically, we need psychometrics to develop and execute tests. Tests in the form of a survey. So you basically, you have there, and we talked about this in, I think it was the second class, we talked about the Rorschach inkblot test as a debatably reliable, debatably valid test. So now you basically, you want to quantify reliability and validity. And you can do this. So again, valid is, does that test really measure what I wanted to test? Reliable is, if I measure it today and I measure it again tomorrow, will it still yield the same result? So this is basically the distinction between reliability and validity. So now you can quantify that. So reliable measure is consistent. Test, retest reliability refers to whether the scale being used provides consistent information every time the test is taken. So you measure your height on day 1 and you measure it again on day 3, it should still be the same height. Otherwise, you have a terrible measure. So this can be basically also be measured with one test. Let's imagine a survey. You have 100 questions. And you can test now, you take from these 100 questions, you label, you take only the odd numbers and the even numbers, and you split your test in half. So now in a perfect world with a reliable survey, you would basically have with the odd questions and the even questions, you would basically get to the same result. So these results of these two sets of questions should basically yield the same insight. If that correlation is not given, then you're essentially looking at a non-reliable test. And there's, of course, a test for that. And the test is the so-called Cronbach's or coefficient alpha. So whenever you do a test, you want to test the internal consistency or reliability of the test. And you're doing that by exactly that, by basically taking an average of those split half correlations. So you use that survey now, and let's say 20 people, you basically get these correlations, and based on that, you can utilize Cronbach's alpha as a numerical method to actually get an overall insight into how reliable that test is. This correlation of the Cronbach's alpha can essentially vary from 0 to 1, with usually in most tests, a Cronbach's alpha greater than 0.7 is considered acceptable. Lastly, a valid measure is basically a measure that assesses what it was designed or intended to measure. So correlation is used to calculate validity often by correlating the measure with existing measures known to assess the variable of interest. So what does that mean? So if you have a survey that gives you an insight into something that is associated and you know to associate with a second variable, let's say, for example, age. People that are older, they're more likely to have some lower quality of life perception. The perception of general health is not as low. So you know there's an external kind of confirmatory variable. And if you find a correlation between a survey marker that is very distinct to correlate with an external variable, you would find your survey confirmed in terms of validity by finding a correlation between these two variables. So that would be the survey result and age, or survey result and, I don't know, it could be how often do you wake up during the night and you associate it with some blood pressure marker or some associated clinical characteristics. So whatever you think in your hypothesis where one marker would correlate with the other, and you find indeed in your survey this correlation that confirms your belief in the validity of your test. Lastly, Nolan and Heinz want to make here the point that most magazines and personality tests you will see in, so most personality tests in magazines and newspapers that you will see are basically useless and don't really help you anything to establish anything about personalities or whatever other claim they're making. So these personality quizzes are really not personality quizzes. It's more like an exercise to be done on a Sunday morning with coffee, nothing else. So they're not really a psychometric test, so to say. So psychometric tests actually undergo a very long process of being developed. There goes actually a lot of thought work into these surveys. Of note, not only thought work in terms of what is it asking for, there's also a lot of thought work about cultural context. There's a lot of context about language, because if you want to have a test that was developed, let's say in classical example from my work, there's a kidney disease quality of life survey. If you want to validate your kidney disease quality of life survey in a population in the US, first of all, you need to translate it from Dutch to English. Then you need to understand the cultural context, because the Netherlands are culturally different from the US. Then you need to understand, do the words, how I translated them, have a meaning that is basically making one response over the other more favorable for a respondent. So there are many different dimensions you need to take into account. And particularly when it comes to psychometric tests, this cultural component, language component, biological sex component, gender components, these play a major role in your validation process. So essentially you will find, if you go through the literature about any survey that you're interested in, whatever it may quantify, you will find definitely a validation study for pretty much every of the big surveys. You will find a validation study for the use in every specific countries. And there's a lot of effort goes into validating surveys before they're being used on a larger scale in different countries. So just as some interesting examples, I used to have, but I think this comes on the next class, was regression. So there are very famous surveys that you will certainly hear about, go somewhat close, or if you go in the direction of psychology, for example, you will hear a lot about surveys. So quality of life is a very traditional, very famous survey that is quite often reported. It's always been validated in pretty much all the languages you could think of. Of note, if you look at the National Health Examination and Nutrition Study, the NHANES, which is one of the largest population health studies in the world, conducted by the CDC in the US since the early 1990s, you will have quality of life of US citizens on American soil, which is super interesting data when you think about it. And there are wonderful papers published. This being said, another survey I could think of, I could tell you about, is the Beck Depression Inventory. It's a survey that was developed in clinical patients that basically gives us degree of a likelihood of depression being present. Above a certain threshold, the patient is considered to be at a higher risk of actually having major depressive disorders. And these are just the surveys that essentially are clinically valid and clinically quite widely used. Any questions on surveys? I'm not a psychologist, so I can't really talk long about surveys, but that's pretty much my 5 cents to the topic. Any questions? So, just to briefly recap, keep in mind, correlation is not causation. you have positive and inverse correlations. You quantify them with a correlation coefficient, which is either small, medium, or large, which is 0.1 to 0.3, 0.3 to 0.5, or greater than 0.3. You need to pay attention to spurious correlation and to unaccounted third variables that may affect your correlation and that associate with both the exposure and the outcome. That's the context of ice cream and drowning. This could be the temperature, the ambient temperature, or the time spent in the pool. So all these things could affect your outcome and at the same time associate with your exposure. The correlation coefficient basically is determined by the product, the sum of products between deviations from the mean of X on the X variable, deviations from the mean of Y of the Y variable, divided by a Markov variability, which is the square root of the product between sum of squares of X and sum of squares of Y, which is calculated in the same fashion as we've always calculated it. Hypothesis testing is in the same fashion. You start off with a scatter plot, and the scatter plot is a wonderful way to pick data. Because the beauty of scatter plot is that you really see each individual point. Each individual point is one of your participants that have answered your question or that were part of your assessment. So you see these relationships already reflected in your scatter plot, and this can then further be looked at with a line of best fit that we've talked about in the graphical displays section. And that already gives you an idea in what direction your trend is pointing at. We will learn, next time we will learn about the R squared, the proportionate error of, proportionate reduction of error. Because when you think about it, if you fit a line through that, and you literally use your dependent variable and your independent variable for the prediction of parameters, you can literally develop a linear function through that entire scatter that allows you to quantify a prediction of how much the exam rate will drop with each time that individual is not coming to class. And this is predictive analytics. Because when you think of the outcome of exam grade, and I'm just quickly giving you a little bit of a taste of what we'll be discussing on next week, Monday. So when we have here a line of best fit, a regression model can essentially give you an estimate of how much that grade will drop. So when you look at this function, and I hope you all remember from high school how to look at linear functions. And that's basically the function of a line. Function of a line has two components, actually three components. So it has a y, which is your y-axis. It has a so-called intercept, which you see here after the plus sign. The intercept is essentially where this line goes through the x-axis. So when you follow this line, all the way to the y-axis, and when the x equals 0, you basically find your intercept. That's right here. That's at 94. So if you enter here 0, and you calculate minus 5.4 multiplied by 0, this drops out. It's only y equals 94.26. So that is your intercept. And you have then here multiplied with the x, which is here 1, 2, 3, 4, 5, 6, 7. You basically have the so-called slope. And the slope is basically the decrease of this function to 1 unit of increase of your x. That means, forget about the intercept, but if you miss one class, your grade is dropping by 5.4%. That's the implication of the slope. Of note, you can also calculate that. You can calculate it by hand, essentially, by knowing the actual value. So let's look, for example, here at exams rates through. That's 3 absences. That's 80. So let's say we have 3 absences. That's 80. Then we have 4 absences. We're just eyeballing this. Let's see, at 4 absences, no, that's actually a little lower. Let's do 75. That's the average between that one and that one. Let's say it's 75. 3 absences. Now we do 4 absences. That's 80 and 68. So 80 and 68, that would be, yeah, let's do a little lower. Let's say it's 73. So we're looking now at 2 values, and no, actually, no, not good. It should be 5.4. So let's see, our 4 absences are now 69.6. So that's the decrease. That's the decrease from 3 absences with 75% to 4 absences, decreasing by the slope that we have in our linear function. So now one way how you can calculate this is essentially by slope k equals your y2 minus your y1 divided by your x2 minus x1. What is that now? So that's basically the difference between your y2, which is 69.6, minus the y1, which is 75, divided by x2 minus x1. Your x2 is 4 absences. Your x1 is 3 absences. So to put this now into context, so you have, so this is the formula. So you have now an x1, x2. You have here in front. This is a y1. This is a y2. So now your x1 and x2. This is 3 and 4. So now your slope will be calculated as k equals 75 minus 69.6 divided by 4 minus 3, right? So we have our y2, that's absence, minus our y1, that's 75, divided by 4 absences minus 3. So the final calculation essentially is 75 minus 69.6 divided by 1. That's 5.4. So that is our slope. Should actually be 69.6 minus 75. My bad, because it's supposed to be a negative slope. So that's basically how you can calculate that slope by hand without having to go over regression equation. But this is how you have to think about slope. So your slope, and this will be important for the homework. These calculations are important for the homework. So basically you have a decrease with each unit of increase on your x-axis. That's your slope. And this at the end is basically just giving you that y value where the function crosses with the y, where x equals 0. So if you want to predict now, so now we spoke about extrapolation and interpolation. So if you want to extrapolate now your function And let's say you want to extrapolate up until an absence of 9. How would you do that? You have your formula. Your formula is y equals minus 5.4 multiplied by x plus 94.326. So now your y for 9 absences, y 9 absences, is minus 5.4 multiplied by 9 plus 94.326. Right? And at that point, it's simple because the only thing you need to do is now punch this into Excel as minus 5.4 9 plus 94.326. So somebody who misses 9 classes is predicted to have an exam grade, exam score of 45.726. Simple, right? But this is how you get now. But this is how you can utilize those insights from your data, and you bring your data to work, because now you use your data and your estimate, your model. This is model. This is a so-called regression model. And we will talk about this in more detail on Monday. This is how you can predict in that way a cross-sectional outcome. But if you use longitudinal models that basically look at the time series over time and take time into account, you can predict the future. And that's basically, you may have heard of building statistical models for the stock market. That's what these guys are doing. Obviously not as simple, but this is basically what is being done. And the prediction of various application use cases. So stock market just being one. It's like we basically use this, for example, we are using this to predict the outcome of our dialysis business. We're calculating a risk for a patient to die next week. And those patients that are basically at the highest risk, we're going to flag and we're going to have a closer look at them. So this is how this can be used and utilized for really important purposes. That's why regression is just really wonderful tool. I highly flag it. Good, but I think we are close to the end. Have a nice weekend, and we're going to see you on Monday. Thank you.